So we just did LeChat's principle and changes in concentration of reactants and products. Now let's do LeChat's principle in terms of changes in volume and pressure for reactions involving gases. So, and the first thing I want to say here is that this is an issue when the number of moles of gaseous reactants does not equal the number of moles of gaseous products. And you'll see that here in this example we're about to do, we have 2 moles of nitrogen dioxide and just 2 moles of gas and just 1 mole of gas on the product side. So this is a great example, great yet relatively simple example. And when you change, there's a change in pressure due to changing volume, or it could just say increased pressure. Well, it's going to be changing volume because when you change volume, you're going to be changing the pressure of all of these. So for example, if we were to decrease volume, so when we decrease the volume, and we've got a picture of a beaker over here, and I'll run a video, this is a video too in a minute, but if we decrease the volume, that increases the partial pressures of all gases. Okay, so that's the first thing, and that's from our chapter on gases. If you decrease the volume, that increases the partial pressure of all gases. And now, before we talk about specifically LeChat's principle, let's return to QC versus KC for a second. So our QC expression has our product on top and our reactant on the bottom. And let's assume that all of the pressures are 1 atmosphere. So QC equals 1, and we're at equilibrium. And then we decrease the volume and increase the partial pressure to double all of the partial pressures. So cut volume in half. Doubling pressures. So now QC is going to equal 2 over 2 squared, which is 1/2. And so let's assume they were all 1s up here, and KC equals QC equals 1. We double all the pressures. Now QC is less than KC, and the reaction shifts towards products, shifts right. Okay, and that's plugging some simple numbers in. Now let me talk about LeChat's principle. Remember, LeChat's principle says we're at equilibrium, we're on a balanced seesaw, and then we are increasing the pressures or doubling them, however it's simple. So increasing is fine. So then we're going to draw 1 arrow for each mole of gas. So I'm going to do here, here, and here. And so it's like double the effect on the reactant side. Our seesaw now is weighed down on the reactant side, and the reaction must shift right. So you can totally do it QC way, you can totally do it the LeChat's principle way, whichever way you want, that tells you that when you increase pressure by decreasing volume, the reaction shifts to the right. And now let me show a little video that also shows this effect.
Nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure. Nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium.
So good, it's almost worth watching again. And so what you might ask, what is the system, how does it reestablish equilibrium? Well, it will actually decrease the number of gas particles as it moves, so every 2 will be converted into 1, overall decreasing the total pressure. So that's changes in volume and pressure for gases. There's a couple of complications to that. So if the reaction involves no change in the number of moles of gas, then there's no effect on composition of the equilibrium mixture. So if you draw arrows and there are the same number of arrows on each side, no effect, no shift in equilibrium. For heterogeneous equilibrium, and so heterogeneous just means different phases, and particularly including solids and liquids. So the effect of pressure changes on solids and liquids can be neglected, meaning no arrows and no effect on QC either, because they don't appear in QC or KC. So the volume is nearly independent of pressure, no changes there. Change in pressure due to an addition of an inert gas. An inert gas may add total pressure, but there will be no change in the concentrations or the partial pressures of the species in the equilibrium constant expression. So an inert gas is a gas that is not in the Kc expression. So, of course, and I say that only because we will see this shortly, so it won't appear in the Kc, so it can have no effect on the equilibrium. That's what an inert gas is. An inert gas is a gas not in the Kc. Let me add this, because it's not in the reaction. Because it's not in the reaction. So, no change on the composition of the equilibrium mixture. Now, let's talk about the last type of change, changes in temperature. And again, this is specifically for exothermic or endothermic reactions. And an exothermic reaction is exothermic no matter what the temperature is. Same thing for endothermic reactions. And we're going to go back to when we were talking about the sign of delta H. And it says you should think of heat as a reactant. For endothermic reactions, which is something we've done before, and we should think of heat as a product for exothermic reactions. And I'll show you what we need. And for LeChat's principle, you add heat to an equilibrium mixture. Adding heat is going to increase temperature. And changes in temperature should be considered the stress on the reaction. And changes in temperature should change here's an analogy, but it's like it's changing the concentration of heat. And changes in temperature do not change which side of the equation the word heat ends up on, because a reaction is either endothermic or exothermic. All right. So here we have an endothermic reaction. In what direction will the reaction shift if the temperature is increased? So here's my process for this one. So N2 plus O2 plus heat goes to 2NO gas. We're at equilibrium. We add heat. Temperature is increased. Is add heat. It's the only way to increase the temperature. Add heat, add energy. Well, I guess we can write heat energy here because it could say add energy as well. Anyway, so whenever we add something, the reaction shifts to take it away. This reaction shifts right. To reestablish equilibrium. This reaction has a negative value of delta H. In what direction will the reaction shift if the temperature is increased? Well, here we have heat on the product side. We add heat, and the reaction shifts left. To reestablish equilibrium. Now, we looked at this video back at the beginning, and now we are going to ask the question, is the following reaction endothermic or exothermic? Let's watch the video again.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
So, let's see what we got here. Reaction. So we added heat, and the reaction shifted left. And we know that it shifted left because the solid went back into solution. Solid dissolved. And this is a dissolving reaction. Well, it's the reverse of a dissolving reaction anyway. So let's see. I'm going to guess that if we add heat here, and we add heat, then yes, the reaction should shift left. So guess reaction is exothermic. That means we add heat as a product. And that, so reaction shifts left. When heat is added, consistent with observations. Reaction shifts left when heat is added. Consistent with observations. And what we just did was we took away a solid, and if you've ever had precipitates in your pipes or things like that, then cleaning pipes is one potential application of how to manipulate equilibria to get reactions to occur or not occur that you would like. Now, it's worth noting that a change in temperature always changes the equilibrium constant. So the equilibrium constant, let's see. Let's take a simple example here of a reaction going A to B, and this reaction is exothermic. And so what we might imagine is that, let's see, A to B is an exothermic reaction. Heat is added. Or temperature is increased. And so, like we've said, the reaction, well, let's see, plus heat, reaction shifts left. That's what we've said so far. And if we now write our equilibrium constant for this process, products over reactants, Bill. If we now write our equilibrium constant, and if we have, let's see, so we're at equilibrium, and then we add heat, reaction shifts left. Well, so our concentrations didn't change. However, because the reaction shifts left, our new equilibrium K value, Kc, constant Kc, must be smaller, must be lower, smaller. Okay, and so our conclusion is that Kc decreases as temperature increases for an exothermic reaction. And likewise, we can say that Kc increases as temperature increases for an endothermic reaction. Kc increases as T increases for an endothermic reaction. Now, the point of this is that if you want a reaction to go faster, you will increase the temperature. That's what kinetics said. If you want a reaction to produce more products, and so then if it's an exothermic reaction, which most reactions that we're interested in are, so you are going to get less product as temperature increases. Kc is getting smaller. So you raise the temperature, your reaction gets to finish or equilibrium faster, but that equilibrium has less products that you were trying to make. Always fun things to keep in mind when you're trying to balance getting enough product to be made, your reaction rate per time, with the position of equilibrium.